Hello Year 12, today we're going to look at the idea of exchange particles, particle interactions, and we're going to illustrate them using what's called Feynman diagrams. We'll start off with quite a straightforward one, the electromagnetic force, and we're going to look at this in the context of two positive protons interacting with each other. So when they interact with each other, they'll come close to each other and they'll repel one another. A proton on the left is still a proton, the proton on the right is still a proton. All that's happened is a force has been exerted. We understand these interactions between particles using the idea of exchange particles. So something must have been exchanged between these two to act upon them. Imagine two people sitting on wheelie chairs opposite one another. If they have a big heavy bag and one person throws the bag towards the other, the person throwing will be pushed backwards by the act of launching the bag. Then when the other person catches the bag, they'll be pushed in the opposite direction by the bag. So they're not pushing each other, there's something that's carrying the force. When we're talking about electromagnetic force, we use the virtual photon. So we spoke a little bit about photons earlier this week and last week, and we say they're virtual because we're not able to detect them, and we represent an interaction using an exchange particle by a wiggly line, and that's the symbol for a photon. So this diagram I've drawn here is called a Feynman diagram. We don't need to know about labels on the axes, but it's also always nice to understand what's actually been shown. So time usually goes on the y-axis, so as time passes in this direction, this is what happens, and sometimes you might see it illustrated with space on this axis, but not always. So all we're interested in is what I've drawn there. So we have two protons interacting, and the virtual photon is the exchange particle. If we move a little bit lower in the direct instruction, I've just included a bit of text I've taken from the textbook. So I'm going to give you a chance to read this in your own time. It basically talks about what force must be responsible for beta minus and beta plus decay inside the nucleus. It involves the neutron. The neutron doesn't have a charge, so we can't use the virtual photon, so it's not the electromagnetic force. It happens inside the nucleus, so we call it a nuclear force, and it's not as strong as the strong nuclear force because it doesn't affect stable nuclei. But again, have a read through that yourself. We believe that the exchange particles are things called W bosons. Again, we don't need to know loads and loads about this, we just need to know that their existence explains what we see. We also need to know that they have a non-zero rest mass. So they do have a mass of something, whereas our virtual photon has zero mass. They have a really short range, so 0.001 femtometers, and as we remember, 1 femtometer is 1 times 10 to the negative 15 meters. They can be positively or negatively charged. So we'll move on to the first of the weak interactions that we need to know about. The two particles that are reacting in this instance, or interacting, not reacting, I beg your pardon, are the neutron and the neutrino. Neutron's represented by a lowercase n, and neutrino is represented by a v, and I've tried to kind of draw it in italics, so it's kind of a curly lowercase v. And they interact with one another, and we'll use that wavy line to show that interaction. And the interaction of the neutron and the neutrino causes the neutron to turn into a proton and emits a beta minus particle, an electron, in the process. It's definitely the weak force that's causing this, but we need to decide whether it's a W plus or a W minus boson. So we have our neutral neutron and it's turning into something positive, so we must have taken away a negative charge and kind of moved it over to this side. So what's actually happening is this interaction causes W minus boson to be emitted, and that decays to form our beta minus particle. So again, this is our electron. You might notice that on this side of the interaction the charge is 0, and if we look at the top of the reaction, your proton is positive, your beta minus particle is negative, so the overall charge over here is also 0, so charge is conserved in these interactions. And as we look into particles in more detail, we'll have a look at what properties are conserved and what are not conserved in each interaction. So we're going to move on to the second part of the direct instruction here. So there's a lot to go through, so it's over 2 pages. We're going to look at proton anti-neutrinos now. So we'll start off with a proton that interacts with an anti-neutrino, and again a curly lowercase v as best we can, and to show that it's an antiparticle, I'm just going to put a bar above it. So if you've got a bar above something, that means it's an antiparticle, so it's an anti-neutrino. This interaction between the proton and the antineutrino causes the proton to turn into a neutron, emitting our W boson. So we've gone from something that's positive to something that's neutral, so this W boson must be carrying the positive charge, and then that decays into our beta plus. So this is our positron, so it is kind of an anti-electron. Next thing we need to know about is beta minus decay. This happens in neutron rich nuclei, and we start off with a neutron that gets converted into a proton. So we spoke about this last week, I think it was. So the proton number of the nucleus will increase by 1, but the mass number, the nucleon number, will remain constant. This emits our W boson, which then decays into a beta particle and a neutrino of some sort. Let's see if we can figure out what charge it's taking away. So it's neutral over here, this is positive, so we must be taking away a negative charge, so that's W minus, meaning that's a beta minus. This is a lepton, that means we must have an anti-lepton down here, and again we've got a few lessons that are going to talk about why it produces an anti-neutrino rather than just a neutrino, but just for these purposes we'll just learn it by rote. So note that this isn't caused by the interaction of anything else, this is just because there are too many neutrons in the nucleus. There's no particle incoming to cause this interaction to take place. We'll have a look at the opposite this time, so beta plus decay, starting off with a proton. That changes into a neutron. That positive charge is being carried away by the W plus boson, decays into our beta plus, our positron, and this time it's just a normal neutrino, not an antineutrino. And lastly, we have the phenomena of electron capture. So in certain proton-rich nuclei, a proton can capture an inner shell electron from outside the nucleus. So we've got our two particles that are interacting. One is a proton, the other one is an electron. I'll draw it as an electron rather than a beta minus particle because it's coming from the electron shells, but it's still negative. We have our interaction. Proton turns into a neutron, that means we're taking away a positive charge, which means that we're going to produce a neutrino over here. And I think that is all of them. Thank you very much.